Today's class. Power losses in transformer. In a transformer, there exist two types of losses. The core gets subjected to an alternating flux, causing core losses. The windings carry currents when transformer is loaded, causing copper losses. First, let us discuss about core loss or iron loss. Due to alternating flux set up in the magnetic core of the transformer, it undergoes a cycle of magnetization and demagnetization. Due to hysteresis effect, there is loss of energy in this process, which is called hysteresis loss. It is given by the formula Bm to the power of 1.67 F into V in watts, where Kh is hysteresis constant, Bm is maximum flux density, F is frequency, and V is equal to volume of the core. The induced EMF in the core tries to set up eddy currents in the core and hence responsible for the eddy current losses. The eddy current loss is given by eddy current is equal to K suffix E Bm square F square T square watts per unit volume, where Ke is nothing but eddy current constant, where T is the thickness of the core. As seen earlier, the flux in the core is almost constant as supply voltage V1 at rated frequency F is always constant. Hence, the flux density Bm in the core and hence both hysteresis and eddy current losses are constants at all loads. Hence, the core or iron losses are also called as constant losses. The iron losses are denoted as Pi. The iron losses are minimized by using high-grade core material like silicon steel having very low hysteresis loop and by manufacturing the core in the form of laminations. Next, coming to copper losses. This is about core losses, that is hysteresis loss as well as eddy current loss. You can see here the eddy current loss as well as hysteresis loss. Next, coming to the copper loss. Copper loss or I square R losses. The copper losses are due to the power wasted in the form of I square R loss due to the resistances of the primary and secondary windings. The copper loss depends on the magnitude of the currents flowing through the windings. Total copper loss is equal to I square R. Here, total copper loss is equal to I1 square R1, I2 square R2. The copper losses are denoted as PCU, P suffix Cu. If the current, what happens? In case the current through the windings is full load current, we get copper losses at full load. If the load on transformer is off, then we get copper losses at off load, which are less than full load copper losses. Thus, copper losses are called as variable losses. Copper losses are proportional to the square of the current and square of the kVA rating as voltage is constant. Thus, for a transformer, total losses is equal to iron loss plus copper loss. The copper losses are kept minimum by designing the windings with low resistance values. Next, coming to efficiency of the transformer. The efficiency can be defined as, because you know that how efficiency will be defined. It's nothing but output power by input power. Due to the losses in the transformer, the output power of a transformer is less than the input power delivered. So the efficiency of any device is defined as the ratio of power output to power input. So for a transformer, the efficiency can be expressed as efficiency is equal to power output by power input. Now power input output is nothing but V2 I2 cos phi, whereas power the transformer supplies full load current of I2 and with terminal voltage V2. Then how do you say copper loss? Copper loss is nothing but copper losses on full load is given by I2 square into R2. Like that, we can get the efficiency as we have seen, as we are seeing on the screen. You can calculate the efficiency by using the formula as such. So this is about, here you can you can see that the copper loss is how actually with respect to the load, how it will vary. The losses, total losses with respect to load, how it varies, it's shown here. Like that, let us calculate how efficiency can will be calculated in transformer. We will see in the next class.